Hello class and welcome to chapter 8 where we will discuss solving systems of linear equations. First, systems of linear equations in 2 variables and then in 3 variables. Okay, so to solve any systems of equations means to find the common solution to all equations. Okay, so what do they all share in common? So as you see right here, a system of 2 equations in 2 variables, we're looking at 2 equations and each of them has 2 variables. So we're looking for the common solutions. In other words, for the x's and y's, they will solve both the first equation and the second equation, right? Okay. So really what we're doing when we're solving these equations, we're finding the common points. We're finding the intersection points, whether it's 2 equations, 2 variables, 3 equations, 3 variables, and so on. Now, in the case of a linear equation in 2 variables, what we are crossing is 2 lines because as you remember from previous chapters, I believe it was chapter 2, the solution to an equation in 2 variables are infinitely many, and all those answers are going to be on some kind of a line. And we're going to solve this system right here by graphing in a minute, but for now, in general, one of the equations is giving us a line. The second equation is giving us a line. So what we're looking for is definitely this common point. So 2 lines, if they do cross, they will cross in 1 point only. So we will only get 1 solution. And that solution is the intersection point between these 2 lines. So we will get as a solution an ordered pair x comma y. Now, if I were to think what else could happen to 2 lines, as you guessed it, definitely 2 lines, it's very possible that they don't meet at all. In other words, we have parallel line, and therefore there's no intersection point, so therefore there will be no solution to the system, okay, because there's no intersection point. And there's yet one more situation. And you might be wondering what it is. Well, here is one line. I go and draw the first line. And there's the second line, and I go and draw the second line. So as you see, what we're dealing with is the same line that we get for both the equations. So basically, both equations have the same solution. They lead to the same line. Well, these 2 lines, as you see, have infinitely many crossing points as they are overlapping each other. So we will get in this situation infinitely many solutions. Okay. So whatever method we're going to use to solve these systems, what we expect from a system of 2 equations in 2 variables, linear system, is either 1 solution, no solution, or infinitely many solutions. Okay, so here it is. Let's solve by graphing. So this is our first method. Now what I'm going to do is take each of these equations on the side. And if you remember how to draw lines, we could solve for y and use the slope and the intercept. Or we could just find the 2 intercepts. So if I substitute 0 for x, then I easily get the y is 2. And if I substitute 0 for y, then I easily get the x is 2. Okay. And I'll do the same thing for the second line. Again, you could solve for y, get y by itself. It doesn't take that long. And use the, so this is what I mean. To solve for y, you get x by itself. This is your y-axis intercept. This is your slope. So there you have it. Right? But we're just going to find intercept. So if I set x equal to 0, negative 2 times 0 is 0 plus y equals to 8. That easily makes y an 8. If I make y equal to 0, then easily x is going to come up to equal to negative 4. Okay, so there you have it. I'm going to just clean the side work away. I'm going to draw both these lines. So 0, 2 is this point right here on the y-axis. 2, 0 is this point here on the x-axis. Now for graphing, you really want to draw as good of a line as you can. The second line crosses at 0, 8. So we're going to be at 8 on the y-axis. And at 4, negative 4 on the x-axis. So when I connect these 2 points, I get this line. Okay. So now I'm trying to figure out where the intersection point would be. So this is what I'm saying. Your lines better be nice and straight and exactly going through the points. Mine are a little off. But my best guess here is that x is negative 2 and that y is positive 4. Okay, so I hope this is a correct answer. Again, my lines were not quite as straight as I didn't have a ruler. So I'm going to check to make sure this is indeed the answer. That's common to both these equations. So is negative 2 plus 4 equal to 2? Yes, it is. Is negative 2 times negative 2 for x plus 4 for y equal to 8? Yes, that's 4 and that's a 4, so that equals to 8. So indeed, this is the intersection point. Okay. All right. So the graphing method is really not quite the best method because even with a nice intersection point that's negative 2, 4, so in other words, it does fit close enough to the origin as in our 6 by negative 6 to positive 6 quadrant system. It comes in a corner. Even with decimals, or if your intersection points is off the grid, you're not going to be able to read that intersection point if the lines are meeting somewhere way out there. And even if they meet, at a decimal point, you're not going to be able to guess that. You're never going to be able to guess, oh yeah, it crosses at 1.37. You won't even see if it was a 1.3. So yes, we do look at the graphing method as it's really what's happening. You're intersecting two lines, so we see how the solution comes about. But algebraic methods are way better. In other words, add, subtract, multiply, divide. So let's solve by substitution. So for this, I am going to substitute. So as you see, this first equation has y by itself. That means this whole expression here can be replaced instead of y in the second equation because my top equation says y is the same thing as negative 3x plus 2. So all I've done in this equation, I replaced y with negative 3x plus 2, and the rest of it I left alone. So now what I have here is a linear equation in one variable only, okay? So distribute in the 4, and there you have it. It's an equation in one variable only. So we've learned how to solve these. What we want to do is get the x's together, get the constants to one side, variable terms to one side. Last thing we do is divide by negative 9, so x is going to come up to equal to 1. Now remember, you have two variables that you have to find. So x equals to 1, yes, we have solved, we had found an answer, but it's not all the answers that we need. We also need an answer for y. So I'm going to now take this x of 1, and I'm going to go back to this first equation that said that y is always -3 times 1 plus 2. So -3 plus 2 equals to -1. Now also do not leave the answer as it is, because our solutions are ordered pairs. In other words, if you were to have graphed both these lines, that's where the lines would have met at. So we always want to write our solutions as ordered pairs. All right, this second system here, even though, yes, we will solve by substitution, the good part of the first system was that y was already by itself, okay? So to solve for by substitution, you need to either have one of your equations solve for x or for y. So I'm going to take that top equation I have, and the easiest variable to solve for would be x. All you have to do is minus the 8y over, okay? So this is how I've changed the first equation. I solved it for x. Now, I've used up the first equation. I'm taking this whole expression and I place it in the second equation in place of x. I'm not going back to the original equation. I've used that one up. So I'm going to the second equation, and wherever I see x, I write that whole expression. So we know that x is the same thing as 43 minus 8y. And so therefore, the second equation can now say 3 times 43 minus 8y, and then continue and copy the rest of the equation, minus 2y equals to -1. So again, what we've achieved here is that we now have an equation that has one variable only. And we know how to solve for that one variable. So I'm going to combine like terms. Minus the 129 over. And now when I divide by -26, I believe that y is going to get me 5, but I will double check. Yeah, it's definitely a 5, I know it. 100 and then 30. Okay. So here it is, we got y, but this isn't enough. I have to find both variables. So I can take this y and go back to really either one of the equations that has an x and a y in it, as we need to solve for x. But really, the easiest one to solve for is the one that already has x by itself. So all I have to do is plug in 5 for y, because now we know that y is 5. So 43 minus 8 times 5 is 40. That's going to equal to 3. So one more time, our solution, written as an ordered pair, is 3, 5. All right. So even though, yes, the substitution method works quite nice, it only is really nice if one of your equation has either just x or y. So in other words, their coefficients are 1. Look at this. To solve this equation for either x or y, you're going to end up with fractions, because let's say you want to solve for x, you need to minus the 5y, divide by 3. So you're going to have to work with fractions all along, okay? So we have another method that would avoid using that. Again, you can solve any system by graphing. You can solve any system by substitution, or by addition, which is this new method. So, as the name suggests it, we are going to have to add something in order to eliminate a variable, okay? So here it is. What we want to do is we want to, if I add these equations as they are now, nothing is going to eliminate. I'm going to get a negative 1x minus 3y equals to 9. That's another equation in x's and y's, okay? However, what would be really helpful if the coefficients in front of x or y are what we would call opposites of each other. So here it is. I'm going to, let me show you, take the top equation and multiply by 3. Take the bottom equation and multiply by 2. So what I mean by this is that every single term in the top equation is going to get multiplied by 3. So this is what we will get. 2 times 3 is 6x minus 12y equals 2. 7 times 3 is 21. Now the bottom equation I multiplied by 2, and I'll show in a minute why. Negative 3 times 2 is negative 6x plus 2y equals to 4. Now what's going to happen if I add these equations as they are? A negative 6x added to a positive 6x gives you 0 x's, yes? And 0 times x, that's just the 0. And then this way, you are now very easily and nicely left with just an equation in y, which will be super easy to solve. All I have to do is just divide by negative 10. Okay. So what made our x's go away? Well, the fact that I put opposite coefficients in front of it. So what we're looking for actually is a common multiple for 2 and 3, which, by the way, are each other, okay? So the easiest way, it's kind of like, hey, how do I add 1/2 to 1/3? I need a common denominator, right? So I'm going to multiply this guy by 3, and therefore the whole fraction. And this one by 2, and therefore the whole fraction. So same thing here. I didn't just multiply the 2x by 3. I had to commit and multiply the whole equation by it, right? All right. So, so what I'm saying is, even if maybe sometimes, just like, hey, I want to add these fractions, 1/4 to 1/12. Well, by the way, 4 already goes into 12, and you just need to multiply this by 3, which works great. But if you can't think of a common multiple for 4 and 12 and know that 12 already is the common multiple, you could multiply by each other, and then you'll make them the same, right? So then they will be the same. So that's what I'm saying. You need to multiply by enough in order to put the same number in front of those variables. Okay, so let's finish this problem and then we'll see some more. Again, what I mean by finish this problem is we've only found y. So pick either one of the equations. It really does not matter. And you can test them both and figure out that you end up with the same answer. And by the way, negative 4 times negative 2.5, that's a 10. So 2x is going to equal to negative 3 once I minus the 10. And then divide by 2. So x is going to equal to negative 1.5. So here is my solution, negative 1.5 and negative 2.5. So if you would have graphed this system by, if you would have solved the system by graphing, the two lines would have had to meet at negative 1.5 and negative 2.5. Let's try this again. Same thing. Easiest thing to do, look, get rid of the x's. They already have different signs, which is what they need in order to add up to 0. Okay. So all I have to do is multiply the first equation by a 3 and the bottom equation by a 4. So that way 4 times 3 is 12, 3 times 4 is 12, but the top equation has a negative 12. That makes them opposites of each other. So negative 4 times 3 is negative 12x. 2y times 3 is 6y. And 3 times negative 10 is negative 30. Multiply by 4. That's a 56. Okay, so as you see, when we add these two equations, we'll get no x. 26y equals to 26, and that easily makes y a 1. Okay. Now take this y and plug it into either one of these equations. I'm going to pick the bottom one this time. So 3x plus 5 times y is 1 equals to 14. Again, I copy this equation, but instead of y, I can now write 1 because we know y is 1. So 3x plus 5 equals to 14. That makes 3x a 9 as I minus the 5 from both sides, and therefore x equals to 3. So take these values and write them as an ordered pair. All right, now I have a few more to try. Okay, so this equation, if I look at it, I immediately see that, again, as I said, 1 goes into 5. So if I just multiply the top equation by 5, I will get exactly to where I want. So a common multiple for 1 and 5 is 5. Okay, so if I multiply 5 times negative 1x, I get negative 5x plus 10y equals to 30. And now I get to immediately add these equations. So basically, I just multiply the bottom equation by a 1, right? I multiply them by each other, but when I multiply the bottom equation by 1, it just stays the same. Okay. And so as you see, this time, everything on the left side canceled out. Not just the x's, but the y's as well. All right. So, however, on the other side, we got 31. So when does 0 ever equal to 31? Well, the answer is never. Okay, so that's never going to be true. That means these lines will never meet, and therefore they will produce no common solution, as this is never going to be true. So we are in the situation as expected. Yes, most of the time we will get one crossing point, one common solution. However, it could very well happen that your lines actually were parallel to each other, and therefore there's no solution to the system. Okay. All right. Now let's try this equation here. It might be a little bit difficult to think about a common multiple. Yeah, you could actually you could also solve it by substitution. So what I'm saying, you could solve for x and plug it into the top equation. Or as I also kind of look at it, you see how this is a 1 and that's a negative 0.2. So if I just multiply the bottom equation by a 0.2, I think we'll get there. So multiply by each other. As I said, the top equation would therefore get multiplied by the 1, right? So if I multiply the bottom equation by a 0.2, I'll get a 0.2x minus 0.4y equals to negative 6. Here, I'll bring down the top equation, which I've multiplied by 1. Yes, so I'm multiplying by each other. Easily done. Don't need to think too hard. Multiply them by each other, and you will get the common solution. And I messed that one up. 3 times 0.2 is 0.6. Now this time, as I handpicked this one for you, no x, no y, all adds up to 0, but also we get 0 on the other side of the equal. So when does 0 ever equal to 0? Well, that's always. So really, what we've had here is the same line. We get the same solutions every time. So we will just simply write infinitely many solutions. Okay. As it's one and the same line. All right, so here's the last one. Plenty of practice. Again, your textbook has a lot of worked out problems. This is not a difficult topic. And this could be looking really bad in terms of, I have no idea what a common multiple for 7/3 is 21/6 might be. So what we're going to do is get rid of these fractions. Okay, so that was my first thought here, get rid of the decimals by multiplying everything by 10. But the fact that this was a 1x, I know what to multiply it to in order to get the point 2. Let me show you something else. So we could do what we did up above and multiply the top equation, in fact, what we've been doing, by 21/6, the bottom one by 7/3, and we will get the same number in front of x every time. Multiply by each other. The thing is, it just if you have calculators, no problem, you can multiply across. But if I could avoid working with fractions, I will. So this is exactly what I will do. I will get rid of the fractions first. To get rid of the fractions, I need to multiply the top equation by something big enough that will reduce the 3 and the 6. So I just multiply by 6. And then I put it underneath. So 7/3, by the way, times 6, which is the same thing as 6/1, is the same thing as 14x. 1/6 times 6, well, that's easy, that's 1. And 2 times 6, no problem, that's a 12. So look at that, I've cleaned up all the fractions. All right, the bottom equation has a common denominator of 12, as you see. So I will multiply everything by 12. Okay. So here it is. Negative 21/6 times 12 is negative 42x. 3/12 times 12, that's just the 3. And negative 3 times 12, that's negative 36. All right, so this is my new and improved system. All right. So again, you can try and get rid of x, you can try and get rid of y. I'm going to look at y, and the simple thing is because the coefficients are much, much smaller. And I already noticed that if I want to get rid of y, a common multiple for 1 and 3 would just be 3. So I'm multiplying this top equation all by 3. So we'll get 3 times 14, which is 42x. 3 times 1y is 3y, and of course a minus, because it's a minus 1. And 3 times 12 is 36. Now the bottom equation basically got multiplied by 1. So negative 42x plus 3y is equal to negative 36. So it stays the same. All right, and if I add these equations, same as the problem before, we end up with 0 equals to 0. So actually, both these equations represent the same exact line. If you were to solve both these equations for y, they will look exactly the same. So they're the same line. You go and draw one, you go and draw the other. Therefore, you get infinitely many solutions. Okay. And this is it. So go practice.